Okay, so here is another example for class 8, and this is pretty close to being one directly out of the book, and I think it is. So we have this set up right here, and the torque transmitted between these two pulleys. We want to find, I guess the torque transmitted between these pulleys if the belt tensions T1 and T2, assume the loose side is 15% of the tight side in T1 and T2. We want to find the reaction forces, the shear and moment diagrams in both the XY and the XZ planes, and the maximum bending moment and location, and the principal stresses and absolute maximum shear stress at the location of maximum moment. Now, when I ask a problem like this, by the way, I'm always frustrated because this type of problem is one I really want you to know how to do, but it takes a long time. So quite often students aren't able to finish a problem like this. So I really highly recommend that you practice it, but I also tend to not ask a full version of this because it takes too long. But I do want you to really, really know how to do this problem. And if I were to find this in the book, just out of curiosity. I want to also mention, if I were to ask this problem, I might ask for find the absolute maximum shear stress and location, and not ask you about any of the other stuff, because you would need to go through a whole long list of things to be able to get to that right there. I want you to know how to do it. I want you to have it, own it. So, by the way, let's see. Where is that problem? Is this that problem? Yes, this is that problem. So that would be problem 371 out of the book if you are trying to make comparisons right there. Okay, so we will, first things first, let's find the torque that's between these two. The first thing we need to do, we could actually do it in different steps right here. One of the first things we could do is to find what the belts are going to be. So let's find what the belt tensions are going to be first. We didn't have to do that first, but I decided to do that first. And which one's bigger than the other one? The one in the foreground is bigger. And we're not going to put in anything with the reactions right there. So the one in the foreground is bigger, so that's the one that actually we want to find. And this is T1, and this is T2. And this right here, they're going up at a 45-degree angle. We're told this is 300 newtons, and this is 45 newtons, right? And we're told what the diameters are, that this one has a diameter, I guess called diameter B, of 300 millimeters. And this one, diameter, this is A, is 250 millimeters. Now, if you do the sum of the moments about the x-axis, because that's this one right here that's coming through, you're going to first, we'll take this one, 300. 300, and we go ahead and use, did I do that? I guess I went ahead and went 0.25, didn't hurt anything. 0.25, 300. So it's positive because this one is going counterclockwise. This one's going clockwise, so it's a negative 45.25, right? Running out of paper. All right. And this guy is T2. Well, it's something we might want to write down. Now, we know that the loose side is 15% of the tight side. Well, which one is the tight side? Well, you could just by observation figure out which one's going to be the tight side. If this one's 300, that's trying to make it go counterclockwise, then it needs, the one that's going to be larger needs to make it go clockwise, right? Because they need to balance out. So T1 is going to be larger than T2. Therefore, T2 is equal to 0.15 T1. You see how that goes, right? They said that the loose side was 15%. So this one, T2, is only 15% at T1. So we could replace that right in there, and now we could just solve for T1, right? So we maybe we start out with T2 is going counterclockwise, so it's going to be plus T2, which is 0.15 T1 times our 0.3, right? Because this is divided by 2, dummy. Right, it needs to be the radius, not the diameter. It's not going to matter because the 2's would have canceled out, but it's good to use the thing the correct way. And then lastly, we have T1 is going clockwise, so it's minus T1 times 0.3 divided by 2 equals 0. So they all need to be equal 0. So we can solve for T1. They need to balance out, and we get 250 newtons, and T2 is going to be equal to 0.15 times that, 250.0 equal to 37.5 newtons. Okay. I don't like that they use T because I like that for torque, right? But we're going to also need the torque that's being applied onto this thing. So in order to find what that torque is, we're going to need to cut the shaft, right? We're going to remember that we can't find torque without breaking that shaft in half and only writing the part that's left over. So I'm going to break it and look at the one that I knew initially. So I'm going to break it right there and then just concentrate on that one spot. So I draw another free body diagram up here and right here, but this time only the shaft is in place right there. So I'll write this out as 45 newtons, and here's my 300 newtons. And here we're going to have a torque. And which way is the torque going to go? Looking from this direction right here, we're going to say that 300 is trying to go counterclockwise. So our torque, that I'll just call T, needs to go clockwise, right? And this is the internal torsion that's inside the shaft that is being a consequence, a reaction of these belts. We also, I might put in, and they would actually look in the other direction, by the way, for this one. This would be over on the bearing side. It would not be in the shaft right there, but it'd be the bearing would be supporting a certain amount of this. There's actually be some within the shaft too, to tell you the truth, but let's not worry about that. Those are just there for aesthetic purposes. So we say the sum of the moments about the X for this. Come on. I don't pay attention a lot of times for that, but when I do, it seems there's always a lot of going out of focus. So I hope not too many of my videos have a lot of out of focus. So 300 is going counterclockwise. So 300 times the radius of this one, which is the let's see, this one was the 250 millimeters, so that's 0.125. This one is going minus 45.125. And then the torque is also minus. So we find what the torque is going to be equal to, and that's going to be 31.88 newtons. All right, so we have this preliminary stuff taken care of. Now let's go and draw the two diagrams that we need for the shear moment diagrams. And these are very challenging for many people, so make sure that you can do it. That's one of the things that I will be looking for when I measure on exams. And I can't find my awesome little ruler. I don't know what happened to me. It's a sad day. A sad day happens when you can't find your little awesome little ruler. Okay, but anyway, I could draw it freehand. So on these, we'll have, maybe I'll want to make sure that you're looking at this in the same way I am. Here is the scenario. I want to look at the XY plane first. So I'm going to look at from this direction right in there. And if I do this XY, see, that's why I need a ruler. Look how terrible that was. Here's a pulley, and here's a pulley. And one of my issues I'm going to have right away is that my forces are at a 45-degree angle. So I actually did the little diagram here, need to go, this 45 has a 31.82 that's going upwards and a 31.82 that's going in the negative z direction. My 300 has 212.1 going upwards and 212.1 going this way. So if you combine those two together, what you end up seeing in the X and Y directions right there, you get 31.82 plus 212.1, and that equals 244.0 newtons. That's what's being applied right there. And from here in the XY plane, you don't see either of these, right? So nothing happens right here. So when we have reactions, it will be a downward reaction happening right there. And so this right here, I'm going to call this Roy because it's at O, and this is going to be RCY happening right there. Some other things I might want to know, transferring over there, that this was 300 millimeters right there, this was 400 millimeters, and this was 150 millimeters distances. I'm going to do collect all this stuff over here for the XZ plane. And so here is X, and Z is downwards, by the way, right there. And we're going to have that similar drawing taking place. And in this case, let's see, I might even use my eraser right there. So in the Z direction, we're going to have that same value, right? So we had 212 coming in that direction, and we had 381.82 going in that direction as well. So that was like this. And it was same thing at 244.0 newtons. But now we're going to see, we're looking down upon this, right? So we're big eyes looking downwards onto here, and the eyelashes are kind of that direction. So we're going to see this thing is going in the positive z direction. So at both of those pulleys together, and it's going to be 250 plus 37.5. So we can actually do that in our heads. Wait, isn't that 287.5? So it's 287.5 newtons happening right there. Now, the reactions of this one, this often happens. The reactions, we might not know the direction each of those reactions are going to have. Quite often, I think of this as the teeter-totter. You're going to have this side over here is going to be ROZ, because he's opposing him, because they're close to each other in magnitude. If they're not close to each other in magnitude, we might not know for sure what direction this one's going to go. But I can tell you from experience that this RCZ actually comes in that direction right there. Really, it's mostly because this one is, they're close to each other, but be on the lookout. You could get the wrong direction when we have these opposing pieces here. Now, I'm going to go ahead and give myself some room. And I might use more paper. Yeah, I'm going to have to use more paper. I'm not going to be able to squeeze everything in there. So we'll just be very liberal with the amount of paper that we use here. So there's the shear moment diagrams that we're going to have, and I'm going to do my statics right underneath it. All right. So I'm going to take the sum of the moments about A, and I did I forgot a couple of things here. And this was A and B and A and B. I guess this is O, and this is D. No, it's C. That would be right. C and O. Okay. So the sum of the moments about O, and technically that's going to be the Z axis. It's going to be 0. So I write out that this guy, 244 going counterclockwise, times my 0.3, and our CZ is going clockwise. RCY, it said Z. And 0.3 and 0.4 is 0.7 plus 0.15 is 0.85. And so we get RCY is 86.12 newtons downward. Sum of the forces in the y direction equals 0. Up is positive. So I get negative ROY, positive 244.0 going up, right? Up. And then I know this is a negative 86.12. So I can see that my ROY is going to be equal to, where'd you go? 157.9 newtons. And it's also down. And it's because this one is so much closer to this one. This one doesn't nearly have to support as much as the of this load as that one, because it's much closer to it. Let's continue with this. Sum of the moments about O, and this is about the y-axis. Right there, right? And once again we have 244, and it's going counterclockwise. And its distance 0.3. But now we have, this one's going clockwise, minus 287.5, and that's times 0.7. And then this one is going counterclockwise, according to what I'm telling you. Now, if we had guessed, we might have guessed that it was going downwards in this figure. And in that case, if we got a negative number, we could see that we chose wrongly. But here, we've already said that it must be that way. And that's the 0.85 equals 0, right? And so if we do that, we get RCZ equal to 150.6 newtons. So I get a positive answer, so I must have done it correctly. And then sum of the forces in the Z direction, downward is that way here, equals 0. So we get ROZ plus, minus. It's going that a ways, and we're saying downwards. At least downwards on the page is going to be, so minus downwards is positive. So this is upward, so it's negative. And then this one is 287.5. Whoops, there you go. And this one is in the negatives direction of 150.6 equals 0. And we get ROS is equal to 107.1 newtons downwards, right? Okay, now we need to use that in our shear and moment diagram. After we've done the statics, we do our shear moment, we start going in our shear moment diagrams. I just didn't like the way that looked. Okay, so for the shear diagram, where we have shear is going to be in newtons. And this is a moment diagram. It's going to be in Newton meters. So we go down by ROY, so 157 0.9. And then we go up by 244, which should be equal to 86 because it's going to come back down. So we get it right to over there. That should be 86.12. And we should check that, right? We should take 157 and subtract out 244 or what have you to make sure that we get this, and then double check, right? So we're making sure that as we're going in a shear diagram, we understand what the values of each of those mean. And then so for here, for the moment diagram, we know that this value right here is going to be negative 157.9 times 0.3. And so what we end up getting is a negative 47.37. And those are Newton meters, right? Because these are meters and these are newtons. So we're Newton meters. We also going to want to know this value. It's easiest to find this. We could subtract out 86 or add positive, I guess, because this is negative. 86.12 times 0.4. If we added that to this, we would get this value. Or we could take 86.12, which is this value, and multiply it by 0.15. And so that's probably what I did. And I got that it's negative 12.92. And now we do a similar thing over here. We take our ROZ, this ROZ. He's 107, something like that right there. So this is 107.1. And then we're going to add, or actually subtract out 244. So that's going to raise us up this high right here. And that's going to be 136.9. 136.9, and then we're gonna and that's gonna be the negative one, right? Because we're saying negative isn't that direction. And then we're going to come on, focus. We're gonna add in 287.5, and that better equal 150. So we got 150.6. I mean, right there, right? Because that's the one that brings it back up, right? So make sure all those things that we want in the shear diagram are all true. Now, we want to find, we know that this is going to have a value right there, right? That's going to be this value. By the way, this is the moment and this is the shear. We should put that a little higher. Shear up here. This value right here is going to be the area of this. 107.1 times 0.3, which comes out to 32.13. Okay, so we could start messing around with this side, but it's going to be easier to come over from the right-hand side. And so we see that it's going to be 0 right here. So it's actually going to come up to right there. And it's going to be 150.6 times 0.15 is going to be this value right there, or 22.59. So we're going to have a crossover somewhere in the zigzaggy one, right? So this happens quite often. So we have moments now at each of these spots. Now we got to figure out where the maximum is going to be. So let's figure out at A. The MA, the moment at A, is going to be the vector sum of these. So we get 47.37 squared plus 32.13 squared. Remember, this is point A and this is point A. They're just two separate planes that are perpendicular to each other. So some diagonal thing is going to go on place. That's going to be the location of this largest magnitude of moment, 57.24 Newton meters. All right, that's in one of the two planes. Now in the other one, I mean, those are the two planes, and now for this other point, we take 12.92 squared plus 22.59 squared, and we get 26.02 Newton meter. So that is the maximum. So we've uncovered that point A is the location where the maximum moment that this beam is going to see happens at point A. So that's where the maximum bending stress is also going to happen, right? So continuing on. Now, after all of that work up at this point, how far did that take us? You know, I'm narrating it, but I'm still doing it. That took me 25 minutes, right, to do all of that. That's why these problems take a long time, because that's just the loads part. Now let's go and do the, let's find the stresses, right? So we go to the stress part segment of our thing. Right? Let's what that goes. Okay. So for stresses, and this is on the back part of my page right here. Stresses in this problem. We will start off with our list. So let's just even write it out. Stress. And we start with axial. 0, right? There's no loads going on in the axial direction, which would be the x direction on this. So they're 0. So we go bending. MC over I. Now, maybe I should have done some of this other stuff. Let's see. What did they tell us in the original problem? Did they tell us the original problem? Should we have read the original problem? Why are we here? What are we doing? Okay. Yeah, if we look really, really, really closely, which you can't see because they just went out of focus again. This is 20 millimeter diameter, right? So over to the side somewhere, I found I was pi over 64.02 fourth, and we got out 7.854 E minus 9 meters fourth, and J was just 2I, which is 1.517 E minus 8 meters fourth. There you go. So here we take that maximum moment we just found, 57.24, and C is at 0.02 divided by 2, I 7.854 E minus 9. Calculated it all out, and we get like 7.288 E7. That's Newton per meter squared, but let's just divide by a million and say that it's 72.88 megapascals. Now we go torsion. Tau, torque, is equal to TR over J. And the torque, you'll recall, we calculated 31.88 squared. Sit down here. Where did I do with that page, by the way? What did I do with the pages that I just calculated? I must have done something with it. Where is everything? There you go. All right. Yeah, so remember up here, we got our 31.88. Okay. And our 0.02 over 2. And our J is 1.517 E minus 8. And what we'll find from that is a 20.29 megapascals. Okay. And transverse, I think the problem should have told us to ignore it. The problem, it didn't say it, but, well, let's actually see in the original problem, right? We looked this up to see, and that was problem 371, and it didn't say it, did it? Power is transmitted, determine the reaction forces, draw a shear moment diagram if needed, one set of horizontal planes and vertical planes. At the point of the maximum bending, determine the bending stress and the torsional shear. Yeah. Didn't really say to ignore the transverse shear, but I'm telling you to ignore the transverse shear because what's going on right there? I think there's a what is that thing right there? I think that's on my camera. Huh. Oh, it's on this page. Oh, there it is. Oh, yeah, it is on the page. Okay, cool. All right. Ignore. When in doubt, ask the professor. But we're going to ignore because it's going to be really small. But it's also difficult to establish because we changed what plane we were in when we got the maximum moment. So it makes it a little more difficult to do. All right, so that right there is going to be what we decided for a stress element, and let's just assume that it's going to be tension, is going to have 72.88 megapascals, and I didn't bother caring what direction I was going to call this right here. We could actually figure it out, and I think this is actually correct as I'm looking at the thing. We could probably have taken this diagram right here and said, well, okay, because this is pulley A, and so if we're looking at this right here, here's the reaction. This is what's coming on to the face of that. So it would be, if this is the, well, this is the x-axis. We can't really say what axis that is going to be in because once again we're not in a plane that's established, one of the standard planes. We've created a new plane. But anyway, that would be I need to just wrap this up. Okay. This would be the stress element that we'd be concerned about. And if we want to go and do a more circle on this, because I asked for, there was principal stresses were asked for, you could either, and I'm looking, once again, I'm looking for my little ruler. Wish I could find it. Where'd you go? I'll use this guy. This nice ruler right here. We'll just do a representation of this thing, right, without being accurate about the values. In the next example, I will get graph paper out and do one from scratch for practice. But in any case, we want to. The first thing we'll do is we'll plot out this face right here. And that face is going to be in the negative, or it's going to be in the lower region here for shear, because it's going counterclockwise. That we know, we make that decision that's how the positive and negative here. And this is 72. So this is like if this was like 20, 40, 60, and so here's going to be the thing, and then maybe we would go 20 and 20, like right there. So we're going to be plotting kind of right there. That's the plot point, would be 72.88 and negative 20.29. That'd be the plot point. The other plotted point would be right there, where we would have 0 and 20.29. That's our plot points for there. So if we're drawing a line in between these two, we get a center that's right there, and we're going to look at a radius that's right here. And if, there's no reason why that this should come out correctly. I'm just guessing, but it didn't come out too bad, actually. So there you go. There is a guesstimate there. I say that C is going to be, it's really just 1/2 of this, because this one is 0, right? So 72.88 divided by 2, 36.44. The radius of this thing is going to be this value, because that's the leg in this case, right there. The tau is 20.29, and that forms this leg right there of that triangle. And so we end up getting 41.71 megapascals, which is going to be the tau max on this one, right? Because we can already see the principal stresses are going to be sigma 1, and this is sigma 3, because this is sigma 2 right in there, right? And so there's going to be itty bitty Mohr circle that's right in there, and then there's going to be a larger Mohr circle that I'm not going to try to do it with a compass, but it's going to kind of come out down. Oh, that's terrible. Maybe I should do it with a compass, huh? Maybe I should attempt it with a compass. Oh, this is going to be ugly. Let's see here. I know it's going to be inside of that, right? No, maybe it's not. No, it's going to be this way, right? No. It's going to be really close. I don't think I can do it. All right, it's going to be something like that. That would be the other Mohr circle, right? I tried to freehand it, and it wasn't going to come out. By the way, right above this is going to be the tau abs max. So we'll make sure that we've, yep. And so sigma 1 is going to be equal to C plus R. That was the formerly sigma A that we would call, which is going to be 36.44 plus 41.71. And so we have 78.15. which isn't all that much different from our 72.88, but it's the largest tensile stress that's going to be into this piece. And by the way, it is tension. Sigma 2 is equal to 0. Sigma 3 is going to be C minus R, and it's going to end up being a negative number, right? So therefore, it's going to be compression, 7.1, and we get a negative 5.27. So sigma 3 is going to be 5.27 megapascals compression. And we know, we could go ahead and we just recognize that R is going to be equal to tau max, or we could say that tau abs max is equal to sigma 1 minus sigma 3 divided by 2, which if you do that, it's almost kind of pointless. But if you minus and the minus 5.27 divided by 2, you get 41.71. No kidding. Yeah, it just kind of, it makes sense from the diagram. But anyway, so, if I'm going to be really thorough, 78.2 megapascals tension, sigma 2 is equal to 0, sigma 3 is 5.27 megapascals compression, and tau abs max is equal to 41.7 megapascals. And there we have a boxed answer for the thing. So this is a really long problem. I've attempted to ask this on exams before, but it's just too much to be able to do in the time frame. And I tend to take a multiplier of somewhere between 2 and 2.5 for the amount of time it takes me to do something for the time that I think that is maybe reasonable for a student to be able to do, or at least, maybe C minus student to be able to do, whatever, necessarily. Slow students are also often make A's, so I wouldn't, not slow students, I meant students who take exams slowly. But anyway, let's see how long this video is. I bet it's really long. Yes, 38 minutes long, right? So you couldn't even finish that. If I double this time, you couldn't finish that in a 75-minute. Now, I did take a lot of detours and that type of thing, but I recognize this is it's a lot of work. So come back to this problem in this video again and again if you are struggling with this problem, because I ask this problem or a version of it quite often, sometimes on every exam. So hopefully this will be helpful to somebody. Thank you.